All right, ladies and gentlemen, we have been talking about le mole, and we know that the mole is a huge number. 1 mole is equal to 6.02 times 10 to the 23rd things. Or in this case, if we're talking about chemistry, we're talking about particles. Little things floating around in our sample. And this is awesome because this allows us to start to have an amount that we can interact with in the lab, because this has been plaguing chemistry for quite some time before Avogadro came along. We got these little things floating around, but they're too small for us to see and they're too small for us to measure, and so we need some way to interact with them in the lab, and our way to do that is with a balance. We now know, using the mole, how many particles are in a sample using Avogadro's number, this 6.02 times 10 to the 23rd, and a balance. As we look, we know that a mole is a huge number. But our mole is not only equal to the number of particles in a sample, our mole is also equal to 12 grams of carbon-12. Wait a minute. That should be ringing some bells. Because what else is set to carbon-12? Yeah, AMUs. We said that one AMU is 1/12 A carbon-12, which means we now have the mass of a proton and neutron. We can find the mass for different atoms in AMUs. And because we set the mole also to carbon-12, now we can start to use a gram scale for our atoms. So 1 mole of carbon-12 is 12 grams. And we know that 1 atom of carbon-12 is equal to 12 AMUs. We see that on the periodic table. Those little averages on our periodic table are in AMUs if we're talking about 1 atom. So for example, if we look at, say, magnesium. You find magnesium on the periodic table. If you had 1 atom of magnesium, it would have an average mass of 24.31 AMUs. There's the average. Now, because AMUs is set to carbon-12, and because our mole is set to carbon-12, we now have an interchangeable relationship. 1 atom would have a mass of 24.31 AMUs for magnesium. A mole of magnesium would have a mass of 24.31 grams. Dun, dun, dun. This is huge. We can work with grams. We can't work with AMUs, but we can work with grams. Now, we give this a name. You'll want to commit this to memory. You'll want to probably make some flashcards. It's super tricky. I love science. We call the mass of 1 mole of a substance the molar mass. Right? Molar mass, the mass of a mole. Sometimes we rewrite this. We'll write it as 24.31 grams per every mole. Now, wait, an equal statement, equality statement, what can we use that to do? We can use that to change units. So now we have a way to go from grams to moles, or moles to grams. Now this was for 1 atom. Let's go ahead and see how this would work for, say, like a molecule. For example, yeah, good old water. It's like the standby. Everybody loves it. You're 3/4 of it. We've got water. We've got an oxygen attached to a hydrogen, attached to a hydrogen. Look on the periodic table. This oxygen's got an average mass of 16.00. This hydrogen's got an average mass of 1.008, so that's a decimal. This hydrogen also has a mass of 1.008. And so if we wanted the mass of this entire oxygen molecule, we'd have 16.00 plus 1.008 plus 1.008. We would add them all together to get a molar mass, a mass of 18.016. Now, if we just have 1 of these little water molecules, which would be crazy impressive because they're so tiny, if you just had 1 of them, it would be AMUs. If you had a mole of water, it would be 18.016 grams. Because they're both set to carbon-12, we can swap them out. And we would rate this, if this was the actual molar mass, we'd rate it as grams per mole. So really, it's 2 hydrogen masses added to 1 oxygen mass. Cool. Now we can use this as a tool. We'll leave water up here for just a second, but I'm going to erase this top part because we need to add our mole train. Mole train, super important tool. I would make sure you've got a special place for this somewhere on your paper. Some students sometimes will put it like on the top or the bottom of their periodic table. Some put it in a special place in their notes because it is super duper handy. We now have the power. We got the power to go from grams to moles, the amount of a substance. And to go from grams to moles or moles to grams, we use the molar mass, which comes right off your periodic table. Good old PT, good old periodic table. Now for moles, it's just the amount of stuff. We can take a step further, we can go down to particle level. Because we know that 1 mole of anything is 6.02 times 10 to the 23rd particles. We use that Avogadro's number. So grams to moles, we use the molar mass. Moles to particles, we use Avogadro's number. And we can go a little smaller than particles, go all the way down to the atom level. And to do that, we count. One atom. Now, sometimes we got some other terms for this particle. We sometimes will use molecule. We'll sometimes use formula, units. These are all interchangeable. Particle, for now, is the same as molecule, same as formula units. Now, the abbreviation, I'm only going to say this once. The abbreviation for formula unit is FUN, F-U-N. Only going to say this once. Chemistry is fun. Abbreviation for formula units is FUN. If you put the other thing, I probably won't be very happy. You don't want to say that to a teacher. Don't put that on paper. Cool. So let's see this in action. We know molar mass of water, 18.016 grams per mole. Let's see this in action. So let's say you went back in the lab, you got a little beaker of water, you set it on a balance, and you found that beaker water has 50 grams of water in it. And here's why this is so powerful. Using these 50 grams, we can actually figure out how many atoms are floating around in our beaker. This is going to be super important when we start talking about reactions and how things start to react and what amounts we need to get a good reaction to go. We now have the ability to figure out how many atoms are actually floating around in our sample. So 50 grams of water, we're starting at grams. We're going all the way to atoms. Looks like there's 1, 2, 3 arrows in between, which means this is going to be a 3-step problem. 3-step problem. We're starting with our first step, molar mass. Well, molar mass, we found it earlier. So it's many grams per mole. Grams are on top right now, so we're going to take our grams, 18.016 grams, equal 1 mole. Grams cancel, we're into moles. Sweet. So sweet. And we know that for every 1 mole of anything, pizzas, if you had a mole of pizzas, if you had a mole of bagels, a mole of pencils, whatever, 1 mole of anything has 6.02 times 10 to the 23rd things in it. In this case, water would be molecules. Cool. So now we're into molecules. We know how many H2Os are floating around in our beaker right now. But we want to take it a step further. We want to know the total number of atoms, how many total atoms are in there. So we're going to take it a step further. We're going to count. In this one water molecule, we have 1 oxygen and 2 hydrogens for a total of 3 atoms. We just count them up. Molecule part cancels. Now, you know times 10 to the 23rd, super huge number. We're going to end up with a really big number here, which makes sense. It does. Atoms are super small. If we're looking at how many atoms are in our sample, our value should be very, very big. Now, if you want to go the other way, you could. You would just flip all your conversion factors so that you're going back the other direction. You can stop anywhere along this train, but if you can go grams to atoms and atoms to grams, you can do any type of problem I throw at you. It's just a matter of finding the numbers that you need from the periodic table and from the compound itself. Cool. Ladies and gentlemen, welcome to the mole train and welcome to our mole calculations. Going to be super vital to us as we move ahead and start looking at our chemical reactions and the amounts we use in them.